I guess using a laser pointer is no good, right? Just use a cursor.
We could find one if you would.
No, it's not. It's
Good. Okay, I'm good. We're live. Okay. Good afternoon and welcome to the Simon's Electron Microscopy Center's Winter EM course. This is our last formal lecture. And is this the title we gave you, or this is the title?
I don't know.
But this is supposed to be misleading, or at least draw out more comments about it. In terms of where we're going in the field is that we're getting higher and higher, how should I call it, resolution, self-consistency, and the wish would be to better interpret our maps. And just having and depositing a density is insufficient. You would want some type of model. And what is that model? And our presenter today is Oli Clarke from Columbia, and he has had a lot of experience in a whole range of structural biology fields, especially in X-ray NMR, and now very well versed in Cryo-EM. So I'll turn over to Oli.
All right, thanks very much. I have no experience in NMR yet, although I'd love to get some.
I saw you poking around in NMR.
Poking around. Oh, I guess I might have been, but I've never done any myself, just with collaborators. But yeah, so today just wanted to give you a little bit of a I guess anecdotal introduction into how to build atomic models manually into what I would call a medium resolution EM map. So that I'm talking like 3 to 5 angstroms. I feel like near atomic should more be reserved for maps like this one here, where you can actually nearly see atoms, where you're more closer to sub 2 angstroms. And if your maps look like this, you probably don't need this tutorial, but and you should take a look at this paper because it's really awesome, I think. You can actually see hydrogens here, which I was debatably, but I think pretty solidly, you can see hydrogens here at a resolution of 1.8 angstroms, which is unexpected coming from X-ray, but it's worth emphasizing because it emphasizes the fact that the maps we look at in EM are not actually electron density maps per se. They're Coulomb potential maps, and they can have different properties in terms of the intensity of different features that show up. So phosphates are going to be less prominent, and apparently hydrogens are going to be a lot more prominent at much lower resolution than we would expect from X-ray. This looks almost exactly like a 2 angstrom neutron map if you compare it. So really interesting. Anyway. All right, is there a way to turn the lights down a little? I can't quite.
Yeah, right behind.
Or is it behind me?
No, where your right hand is.
Anyway, so why do we want to build an atomic model into an EM map? I mean, all of the right, one of these. Well, that's there. That's all. So why do we want to build an atomic model into an EM map? All the information is there already, right? Well, so the aim of building an atomic model is basically to create a compact interpretation of the density map, incorporating prior knowledge. So incorporating what we know about protein structure, protein chemistry, both in general, like we know with a great deal of precision what an ideal alpha helix looks like, but also with reference to the specific case that we're trying to build. So if we have a crystal structure of a protein or a homology model of a domain, then that helps us out a lot. Building an atomic model is still a very manual process a lot of the time. Even if you're at 3 angstroms, 3 to 3.5 angstroms resolution, in my experience, auto-building programs still don't get you the whole way there, or usually even very much of the way. They'll give you some starting points, some fragments which might or might not be correct, but even the best auto-built model typically requires a lot of manual interpretation, manual correction, and manual completion, and manual editing. There'll be a lot of errors that you need to be able to recognize, pick up, and fix. And as I mentioned, this is a trade-off, or rather the level of detail that you can build in an atomic model is going to be a trade-off between the amount of prior knowledge you have for that particular problem and the resolution that you have. So if you have a crystal structure, the exact thing that you're trying to build, it's fine. You can fit it into a 10 angstrom map, no problem. Whereas if you don't even have sequence information, then probably 3 angstroms won't even be enough, because you still won't be able to tell the difference between, for example, a serine and a cysteine, for example. And so the types of prior knowledge that we're talking about and the information from the density map that we need to collate include things like as much information as we can derive from the sequence as possible. So, just the primary sequence itself, but also secondary structure prediction and disorder prediction provide extremely useful constraints when building an atomic model. And the sequence conservation and patterns of, let's say, structurally unique residues. So particularly large aromatic residues like phenylalanine, tyrosine, tryptophan. Unique patterns of those residues are really good starting points for atomic model building, because they can anchor you in the map at a point where you can then extend the sequence through the density. And of course, if you have a crystal structure or a homology model of any domain within your protein, that also gives you a hook, a place to start with and a place to build from. And just in general, all of the knowledge that we have from the PDB, our knowledge of secondary structure, fold identification, and protein chemistry and geometry all contributes to our initial model. And from the density map, we have a complementary set of information. And the things to consider there when determining, how much and what type of information we can get from the density map. The patterns of large side chains that are visible and of side chains that we can't see, because the absence of a side chain in the density also tells you quite a lot. Like if there's no side chain there, it's probably not going to be a tyrosine, a tryptophan, or a phenylalanine, or it's very unlikely that it will be. And we can also gain quite a lot of information that we can use in model building from analysis of conformational and compositional heterogeneity of the sample. For example, if one subunit in a particular class is entirely missing, that can allow us to assign boundaries for the protomer, which is something that at very low resolution, like 4 or 5 angstroms, can otherwise potentially be tricky. All right, so the idea is you want to be taking all of the information that you have available and putting it into building an initial model. And you want this to be, ideally, a unique model that agrees with both the density map and your prior knowledge. And it won't be unambiguous in every region. And I think an important part of this process, which I'll come back to later, is how to deal with ambiguity. Like in regions where you can't be completely confident of sequence assignment, what do you do? And how do you specify and convey uncertainty? The other thing that I want to cover a little bit later is validation, and particularly focusing on local validation and trying to get across the point that validation is like a lot of folks right now are looking at validation as just ensuring that there's no overfitting. And in a way, I think that's probably the least important form of validation for an atomic model in the EM map. Vastly more important is local geometric and model fit to the density map validation. So using mole probity, EM ringer, and just inspection of your map with your model to ensure that you're not over-interpreting things or drawing conclusions that aren't justified by the density map. This is an iterative process. So after building an initial model, refining it into the density, you'll want to inspect it and go back through each part of the model, extend out regions where you've assigned sequence, try to interpret regions where you haven't, connect them up, and ultimately identify a single model which is consistent with and explains as much of the map as possible in terms of both the protein, nucleic acid if present, and ligands that you can identify, hopefully. And that may require collecting more data. It may require, for ligand identification, you may want to collect a data set that's lacking the ligand, calculate a real space difference map, do some other things like that. All right, so before you start any of this process, I think it's important to think a little bit about where you're starting from. So what your map looks like and how to prepare it for model building. So you want to be thinking about both whether you have the best map you can get from your data, and also whether you've applied the optimal sharpening and filtering procedures to it, because it can make a dramatic difference to the appearance of your map. And I personally like to build with multiple maps. So let's say you've got a structure in the resolution range of 3.5 angstroms or thereabouts. I would typically start map inspection and interpretation with a map that I've filtered to around 4.5 angstroms, maybe 4 angstroms, one that's filtered to the global resolution, and one that's filtered to the best local resolution. And I'd have them up simultaneously and switch between them as needed. The reason for that is that in a map that's filtered to a resolution that's too high for the local region, that region's going to become a lot noisier, and particularly the connectivity between different parts of the protein will be compromised. So you'll find in a map that you filter to a resolution below the global resolution, let's say 4.5 angstroms, the connectivity will be much clearer. And also the appearance of disordered regions, which you may not be able to build, but you can still give you information about, for example, the size of the bit that is missing. Those will be much more prominent if you filter to basically, the worst local resolution in your map or nearabouts. For map modification, I would try multiple methods. So simple B-factor sharpening works great. But I find in my experience that the approach used by Phoenix Auto Sharpen has been a lot better in a couple of recent cases. And I think I'm not entirely sure why, but I think it's because that incorporates an anisotropy removal step in that process. And certainly for some of my maps, that's been really advantageous. There's also an option in Phoenix Auto Sharpen for applying a model-free local sharpening procedure, and for a couple of maps that's been really valuable. And I would advise, try them all, see which map you like the best in whatever region, and use them all together to inform your interpretation and your building of the model. And the final point I'd make about that is that trust your eyes. If your map doesn't look like 4 angstroms, but the number that's coming out of your FSC calculation is 4 angstroms, trust your eyes more than the FSC and try to figure out why that is the case. So there are a number of reasons why a nominal resolution of 4 angstroms might not really look like it. Number one would be you've got a substantial orientation bias, so calculate a 3D FSC or use some other metric to analyze anisotropy. The other thing to consider is your mask. Are you using a sensible mask which covers your entire molecule, or have you accidentally, for example, used a map which was auto-generated by a threshold that isn't sensible and only covers a couple of voxels? I've definitely seen that happen, and it can lead to results that are, let's say, over-enthusiastic. And just double check that you're actually looking at the sharpened map, because I've also encountered people who are looking at their map, they think it's sharpened, they go back, they figure out they're actually looking at the unsharpened map where you can't see anything in terms of side chains. And also analyze local resolution. Check that you might find that in the center your map is fantastic and you can see side chains and everything's great, but as you go towards the periphery things get progressively worse. And the other thing is just that figure out at this point whether this is going to be a goer or not, whether you have enough information present in your map to get the biological result that you want. You may not be able to build a full atomic model, and that might be okay. It depends what question you're asking. If you're trying to identify how one subunit binds to a larger complex, you may need pretty limited resolution. But if you're trying to build a atomic model de novo and you can't see enough side chains to unambiguously assign the sequence, you're going to need to go back and either improve the processing of your data set to obtain a better map, or obtain a better map in that region, e.g., for example, using like a local refinement approach, a focused refinement approach, or collect more data. All right, so getting into to map interpretation. I don't know how familiar everyone is with density maps, but like I think a good way to start is to look at what we can learn from just like looking at a map. How much information is there in a local region of I shouldn't say electron density, EM density, let's say. So looking at this, can anyone see anything wrong with this helix, or is there anything apparent from the helix that doesn't seem quite right? Anyone? No, it's fine.
3 residues per turn?
No, it's got the right number of residues, but this one.
How many people have looked at atomic models? Do you know how helix should go?
Is it right or left?
Yeah.
Like,
Yeah, so this one's left-handed, and it should be right-handed. And right here, this is actually pretty obvious because you can see the pitch of your helix quite clearly. But if you're at like 5 angstroms, then that can be pretty tricky to determine. And the reason why I raise this is that if you're calculating a reconstruction of a protein where you're not starting from a reference model where you know the overall chirality of the assembly, you're just as likely to end up with a left-handed, with an inverted hand as you are to end up with the correct hand. So if you're interpreting a map at 5 angstroms or 4.8 angstroms, be really careful of that because it can trip you up pretty easily. All right, so like what else can we learn from this? So the other obvious question here is which direction does the helix go? And so the thing to remember about that, or the way to think about it, I think, is that an alpha helix is like a Christmas tree, more or less, where the trunk of your Christmas tree is at the N terminus, the top of the star is at the C terminus, and all your side chains are pointing back towards the N terminus. And from that, you should be able to determine the direction of this helix reasonably unambiguously, although this one's a little tricky. Does anyone want to point out which way? Do you reckon it's the one on the left or the one on the right? Which way is the helix going, looking at that? That's right, yeah, exactly. So it's this guy, because you can see that you've got this big bulky residue up here that's pointing up, more or less, and same deal with this one down here. You're going to have your helices pointing back like arrows to where you should be coming from. So next question, looking at something like this, is can we identify any starting probable, at least categories of side chains from the density? So if you take a look at this and you're vaguely familiar with protein chemistry, you might say that, okay, so we've got this guy here, looks pretty bulky, could be an isoleucine, could be something larger, could even be a phenylalanine potentially. But this guy up here, this guy's really big. So I would start with that guy and try to figure out what it is. And usually what you're going to do is you're going to try to test a couple of different hypotheses and see where they take you. So we could start out by like trying to see, is it a phenylalanine? Is it a tyrosine? Could be either. We really have to test different ones in the sequence, different patterns that match this density, and then see if by extending the sequence, the results that we get are consistent. And so let's say it is a tryptophan, we can, and there's the actual atomic model in the map. What we have is we have tryptophan there, and the other one, as it turns out, was a phenylalanine, notionally at least. But we can't, we make the hypothesis that this guy's a tryp, this guy's phenylalanine, this guy's a phenylalanine, and that this corresponds to this region in that sequence. Then what we want to do is we want to test whether that checks out. So you want to extend sequence assignment to those other guys and see whether that makes sense, not just in terms of how the larger residues match to the density, but in a way the smaller ones also provide in some sense, even stronger constraint. For example, think about if you had extended that hypothesis and you'd found that you had a glycine at this position in the sequence based on that sequence assignment. You'd know unambiguously that was wrong because there's a big bulky side chain there. And so the negative information that you get from those small residues can be just as valuable for constraining your model as the positive information that you get from the obvious big side chain densities. This is all pretty obvious stuff, but it's just good to go through it. The other thing to note about this, and the other thing to consider when you're building, is that the local information content of a region of the sequence is going to vary. And what I mean by the local information content is how unique is the pattern of large residues, of residues that you can easily distinguish based on the density. So if you just consider your pattern of large aromatics, for example, and you look at this first sequence here, basically all of these residues at 3.5 angstroms are going to look pretty similar. V is going to look the same as T, is going to look the same as V, etc. Whereas this one has unevenly spaced aromatic residues that can only fit one way in one direction. So some regions of sequence are going to be easier to fit than others. And in broad strokes, repetitive strings of small to medium residues are really tricky. And repetitive sequences in general are really tricky. As I mentioned before, I think secondary structure prediction is probably one of the most valuable sequence-derived properties you can use when you're starting out building an atomic model. I really like Extel-Pred, which was originally intended for predicting crystallizability. It doesn't really work for that purpose, nothing really does, but it gives a really great summary of a couple of predicted properties of your protein. So you can see here all the regions that are strongly predicted to be alpha helical are highlighted in red. Those that are strongly predicted to be beta sheet are highlighted in blue, and predicted disordered regions are underlined. And predicted transmembrane helices highlighted in yellow, although there are none here. The reason why I think this is particularly valuable is that secondary structure prediction these days is actually really good. So for any given residue, the secondary structure prediction is about 80% likely to be correct. And that means that if you see a long string of residues in your model which disagree with the secondary structure prediction that you have from the sequence, you want to pay very close attention and check whether you really got it right or not. So it's a great starting point for assigning. Like if you see a beta sheet in the middle of a string of alpha helices, like for example this guy, you can sort of guess just looking at this density map where that is in the sequence. Does anybody want to point it out? I don't know whether you can see the numbers from back there, but you can see here there's just one little predicted beta hairpin in the middle of a whole string of alpha helices. And it turns out that that is actually and it's the only region that is predicted to have beta sheet structure, and it's the only region that does, as it turns out, have that. And as I mentioned, like, secondary structure prediction is pretty good, so use it to guide you. The same, to a certain extent, is true of disorder prediction. That's less, less accurate than secondary structure prediction. But if you see a string of 300 residues that are predicted to be disordered and don't have any predicted secondary structure, you can pretty much place a bet that those guys are not going to show up in the map. And in this case, that checks out. They don't. All right. So this brings us to thinking a little bit about ambiguity. So what do we do when we're not sure? Because you're going to have regions in a map. If you have a map that's an overall resolution of 3.5 angstroms, there are going to be regions that are at 4.5, where you can't be completely certain locally of the sequence assignment. And the question is what you do there. There isn't a super clear consensus on that in the community, but my suggestion would be, or what I tend to do, is assign the residue codes of each residue where you're not absolutely sure what residue it is as UNK for unknown, and assign the numbering of that residue to your best guess value, what you think it is based on the adjacent sequence that's around. This is not ideal. Ideally, we want a more granular way to both convey and quantify uncertainty, because if you think about it, if you have a 1,000 residue stretch of unknown residues, but the starting point is 10 residues away from a bit that you know, then you've probably got a reasonable idea of at least the plus or minus numbering of that bit at the start. But the bit in the middle, you're not going to have a clue plus or minus 100. And we don't really have a good way to convey that as encoded in an atomic model. So, as I say, what I would do is just assign your best guess numbering, but for anything where you're not sure, assign it as an unknown residue, so because otherwise biologists who look at your model are going to assume that you're certain. A PDB looks very certain, and most biologists don't look at the map. The number of people who will download your electron density map is probably 1 to 5, depending on how many people solve the structure. Yeah, so make sure that the model conveys everything that it needs to. The other thing to think about in terms of ambiguity is sidechain placement. When to put sidechains and when not to. There's a couple of caps on this, and they basically come down to trim them back until there's no atoms that are outside the density, or put everything in and do that. There are arguments for both. The argument for trimming the sidechains back is you don't want to give people the idea that you know residue number 59 is in rotamer X when you don't know that. The argument for putting all the sidechains in is that it provides quite a strong constraint on the on geometric validation of your model. If you have a hydrophobic core where you've not placed a bunch of residues, when you analyze that with, for example, mole probity or anything that analyzes clashes, it doesn't implicitly take into account the fact that your phenylalanine should have a sidechain. It's just going to check it naively. And so that can hide modeling errors quite well. So my preferred solution to that would be, at the very least, analyze a model where you've put all the side chains on and check that it doesn't look crazy. And then if you want to trim them down after validation, go for it. The other approach is put them all on there, but change the atoms that are outside of the density or that you're not confident about placement of to zero occupancy. That's another way to go. But again, there's no real right or wrong way to go with that. I would just say it's important that you're consistent in your approach, and ideally that you explain and write down that approach when you write up the structure, which doesn't happen very often, and it would be really useful if it happened more often for anyone who's interpreting atomic models. Okay. So this is just an example of, as I was saying, prior knowledge can come in many different forms, and you should use any and all that are available to guide model building. So this was a case during the initial structure solution of the ranitidine receptor, where we were at 5 angstroms and we weren't entirely sure of the subunit boundaries. And after 3D classification, we fortuitously had a case where one entire subunit of the channel was more or less missing and disordered. And by calculating a difference map between that class and the good class where all subunits were present, we were able to obtain a difference map which gave us much greater confidence that the boundaries which we'd initially assigned for the protomer were actually correct. Because if you think about it, like, if you can't completely tell connectivity, the boundaries for the protomer could just as easily be, the boundary could be, here and here, for example, could be, orthogonal to that. And it's very easy to end up a situation where you have, like, effectively a domain swapped arrangement. You can also get guides to that from analyzing conformational heterogeneity, because subunit boundaries are often going to be a bit flexible, and you can use that to help you as well. And in a similar approach, this was also with the LIR, you can use difference maps to guide your placement of ligands. So in this case, this was a structure of the ranitidine receptor where we had a map where we had 3 ligands present, calcium, ATP, and caffeine, and we had another map where we had none of them present. These were both at around 4 angstroms. And if you calculate a difference map between those two, you can see 3 clear difference densities. I should say that this is not a straight difference map. If you calculate just one map minus the other, you're going to get a mess, because when ligands bind, things move around, and so you need to deconvolute that. And the way you can do that is by calculating a locally aligned difference map. So you can just extract out the density around the domain of interest where you think your ligands are binding, extract that out from both maps, align those 2 densities in Chimera or your map alignment tool of choice, and then calculate the difference map from that. And that'll give you a much cleaner difference density map for for identifying ligand binding in the presence of domain movement. That said, in this case, you can see there still could be some ambiguity. We can see 3 ligands, but we're at moderate resolution. How do we absolutely know which one is which? And for that, in that case, you can just do, what we did was to do pairwise difference density maps. So when you have all 3 minus nothing, you see all 3 peaks. When you have one that has calcium minus nothing, you see a peak only on the calcium. And when you have one that just has ATP and caffeine minus nothing, you now no longer see a peak on the putative calcium, but you still see the peaks on the ATP and the caffeine. And this is really just to show that you can get, in EM maps, you can get really beautiful difference density at moderate resolution. So this is 3.8 angstroms, and from a crystallographer's point of view, it looks much nicer than that. All right, so this is just to introduce the, one of the other major forms of prior knowledge in atomic model building, which is our knowledge of protein stereochemistry. And here that's encoded in the Ramachandran plot, which basically describes the allowed, or let's say geometrically favored, backbone torsions. And the Ramachandran plot is a great guide at the kind of resolutions that we work with in EM. At very, very high resolution, you can justify outliers to the Ramachandran plot, things that are strained and unlikely but happen occasionally, but they have to be justified based on the density. If you're at 3.5 angstroms, you really shouldn't have any Ramachandran outliers, because there's no way you can really justify that the backbone is in a strained conformation if you can't see any of the backbone atoms. So it's basically only when you can see carbonyls, then it would be allowable, I would say, to have Ramachandran outliers. And so different regions of this plot map to different types of secondary structure. This region over here maps to alpha helices, beta sheets, and then you have some odd regions that appear in turns and various other little parts. I should say, in terms of helices, there are actually multiple kinds of helices, not just alpha helices. There are 3 relatively common ones, of which 2 are more common than the rest. So there's your classic alpha helices, which account for about 90% of the helices in protein structures, which have 3.5 or 3.6 residues per turn. And these guys, when you look at them in cross-section, are fat. They're your classic helix. The less common, but still appreciable, particularly in membrane protein structures, variant is the 310 helix. So this is 3 residues per turn, and that helix has a very distinct cross-section. So these guys look triangular when you look at them down the axis. They can be difficult to identify at low resolution, which means they can be, and also programs don't deal with them all that well. So, programs like COOT, for example, will have secondary structure restraints for real space refinement of alpha helices, but if you want to do that for a 310 helix, you got to do it manually. And so that means if you refine a 310 helix, or rather if you refine a 310 helix in COOT, it will often try to turn itself into an alpha helix, and that can lead to register errors. So if you be aware of these guys, watch out for them, because they do come up pretty often. Like the classic example, if you're at all familiar with ion channels, is that the S4 helix in an ion channel, the 4th helix of the voltage sensor, is pretty much always a 310 helix. And it's very, very distinct, and that's really important to its function, actually. So, be aware of these guys when you're building. All right. So the other major type of secondary structure is, of course, the beta sheet, and these can be either parallel or anti-parallel in orientation, with different hydrogen bonding patterns in each case, which you can see described here. More common, I can't remember by how much, but more common anti-parallel sheets. These are a lot more difficult at low resolution to build than alpha helices. And the reason for that is that sheets twist. Whereas alpha helices tend to be straight or at most slightly curved, beta sheets are like a flat sheet which can have a certain twist associated with it. And the individual strands are difficult to place until you get beyond 4 angstroms or so. So they're much harder to build manually than alpha helices. So there are a couple of other considerations when building an EM that we don't come across in X-ray. I've sort of covered a couple of these, but one of the major ones is that we don't have any unambiguous sequence markers. So in crystallography, you can obtain information from anomalous scattering that can tell you unambiguously all of these residues are methionines, or all of these residues contain sulfur. And we don't have that in Cryo-EM, which means that at 3.5 angstroms, things are a lot trickier than they are in crystallography for building. And there's a lot less feedback as to whether you've got it right or not. In crystallography, your phases are generally coming from your model. And if you're improving your model, your phases will get better, your map will get better, and you have an iterative process of feedback and improvement. In EM, you don't have that. You also don't have any model bias, but all you have is your starting map. So knowing whether you've interpreted correctly requires a lot more just sitting there looking at the map and trying to analyze all the different possibilities for a given region of density. and trying to work out whether you can really tell unambiguously whether you've got it right or not. And the other thing, of course, that we don't encounter in crystallography to nearly the same degree is variation in local resolution. So in EM, you will often have a very big variation in local resolution that you just don't see in crystallography. And that introduces a lot more of the ambiguities in sequence assignment that I mentioned earlier, which, they've been a consideration in crystallography since year zero, but they come up much less frequently than they do in EM. In EM, not every, but in most moderate resolution cases, you're going to have some regions that are really tough. And often we have more than one map to build with different composition and different conformation, and that can introduce both, it gives a lot of benefits, but it also gives a lot of complexities. If you have one model to refine against 10 maps, that's a different problem than just building a single model against your only map that you have. So, just to go through where I would start with building an initial model.
Charlie, do you want to change the battery still?
Oh, is this not working anymore?
It cut out. We ran out of batteries.
Oh, right.
Okay.
Sorry, guys.
That's okay. No, it's batteries.
Let's see. Or did it just turn? Oh, it seems to be working.
It's okay. It's fine. Just where your position.
All right, let me see. Is that better?
That's good.
Okay. All right. So where to start with building an initial model? Obviously, if you have a crystal structure or of anything, even if it's a small fragment of the entire assembly, that's your best place to start. Find out where that goes, and that gets you a starting point that you can extend from. If you do have sufficient resolution, let's say beyond 3.5 angstroms, try auto building, but be very skeptical of the results. Assume they're wrong until proven otherwise. Look at them very, very carefully and work out which ones you actually believe. Trim back the auto-built model as much as possible so the only bits that are there are things that you actually think are right, and then extend them. And otherwise, if you're starting manually, you have to basically go through the procedure that I described at the start. So have a look in the sequence for regions that seem like they're going to be structurally unique, and see if you can place them in the map. So look for patterns, unique patterns of aromatic residues, and ones that are going to be in a region of the map that has your best resolution. Try starting with those, see if you can place them, extend, work from multiple different places in the map, and try to connect all those things together. All right, so how do we, in the first instance, if we have a domain, how do we fit it to the map? So I would typically start using Chimera. You can use Pymol or other programs, whatever you like. I find Chimera convenient for this. If you have a good guess of approximately where the domain is, move the model of that domain to approximately the right position in the map. And then in Chimera, at least, there is a command you can use to perform what's basically like a real space molecular replacement operation. And you can see that command written down here. So basically you use the command fitmap, but with the search keyword and the radius keyword. So it would be fitmap, the actual command is here. So fitmap, map model, search 100, radius 5. What that means is fit the model number 1 to the map 0, try 100 different candidate orientations in a radius of 5 angstroms around the center of mass of the model. And when you do that, what you'll get is a list of potential candidate fits, and what you're hoping to see is a clear cutoff in the correlation of the map to the model for the correct solution versus the incorrect ones. And generally when you see that, everything's good. And if you take a closer look, you'll see that the model matches very well with the map, and this is a great starting point for then extending either direction into the sequence and extending the sequence into the map. In this case, this was an N-terminal domain, which is even better because it means we really know where we're starting, and we can extend out into the rest of the sequence. The other point that I would make that's specific to EM, which we don't encounter in X-ray, is that we often don't know exactly what magnification we're working at. So the nominal magnification that you collect your data at is often, depending on what microscope you're collecting on, it may not be right, and I definitely would assume that it's wrong unless, I mean, here at SEMC everything's great, everything's being calibrated, but you know, if it's just being calibrated with like a cross grading, it's going to be off by enough that it's a problem. If it hasn't been calibrated with a crystal structure on, you know, collecting using the same settings, then you need to check it, because it can be off by quite a substantial amount. So here's a case of aligning, you know, both the map that's been calibrated versus the one that's not. And you could see, if you didn't know, you might say these are two different conformations of the same thing. And if they notionally are two different conformations of the same thing that have been published by two different groups, that's kind of a problem. So you want to pay attention to this. Also, when you're downloading maps from the EMDB, pay attention to whether the voxel size is being calibrated or not. Because often it's the case that you can do it yourself even if the authors haven't done it anyway. If there's a crystal structure of a domain of the complex, you can use that to calibrate the voxel size, to calibrate the magnification. And you can actually do that really easily in just using UCSF Chimera. If you take a domain, so actually here what I've done is I've taken this domain, and I've taken this map, which has a notional voxel size of 1.34 angstroms, and then I've fit that domain at different nominal voxel sizes and calculated a correlation coefficient. If you do that and then plot those correlation coefficients, you typically get a really nice curve with a very distinct optimum at the correct voxel size. And I would highly recommend doing that, you know, at least the first time that you're collecting on that microscope at that mag, because it can really make a difference, both to resolution estimates, but particularly, it's usually fine when you're looking at the same structure, because these differences are like 1%, and in terms of geometry, that's not going to make a huge difference. But it does make a big difference. If you've got, you know, 1% of a 400 angstrom structure, that's 4 angstroms, and when you're aligning two structures that haven't been properly calibrated, it means it's really difficult to draw solid conclusions from that comparison. So it makes life difficult. Anyway. All right, so how do we actually build atomic models? I would start using Paul Emsley's program, COOT, which is a fantastic suite for model building. Really, it doesn't have any competitors that I'm aware of for any real competitors that I'm aware of for manual model building at moderate resolution. And it provides a really simple, well, simple's not quite right, I guess, but a really intuitive interface for building and manipulating atomic models and density maps of any kind. And you can run it on whatever hardware you have around. You don't need anything fancy. It'll run fine on an old laptop, no problem, even with big maps. But the thing that I really like about it is it has a very extensive programming interface. So you can very easily write your own little Python scripts in order to modify what COOT is doing and to make custom functions which do what you want, which in EM is often really helpful because, you know, you might be dealing with something that's particularly large or at low resolution, and you might want to modify the way that COOT is working. So as I mentioned, it's got this really useful API. I've written a bunch of scripts for it to customize COOT for EM building. Other people have done the same thing. I'll go through some of the ones that I use and I've written in case they're helpful. And basically, in any case, if you've got a Python script for COOT, the way to run it is you just copy that Python script into this little hidden directory, home/.COOT preferences, and that Python script will be executed when you start COOT. So, and you can use this to make a custom menu to give you extra key binding, shortcut keys, whatever you like. And it's really easy to chop and change and write your own on these things. So this is just an example of some code here, where like here I wanted to write a function that would just mutate a given residue by the entered single residue code. So you hit a key, little box comes up, you click Y, it mutates it to a tyrosine. Just makes it really fast for mutating a new residue when you're building maps. This is really easy to write in Qt because you don't have to write it starting from scratch. What I mean by a programming interface and API is that Qt has a ton of prepackaged functions that you can just use, chain together to do whatever you want with inside the program. Definitions of the active residue where the cursor is, definitions of mutating a protein residue, mutating a nucleic acid, easily bringing up a dialog for user input, all of these such things. Super, super easy. And then you can just tie it to a keyboard binding really easily, so you've got it there to use. All right. As I mentioned, there are a ton of key bindings that already exist, and it's really easy to define your own. And these make everything much faster to do in Qt. When you're dealing with proteins that are potentially in the thousands of residues, the speed with which you build each residue is a big bottleneck. So you want to make sure you're doing things efficiently. And often that means doing a little more work at the start and writing a little script that'll help you do things along the way. And there's a lot of code out there that you can just take, modify, often pretty minimally, and use in order to have it working the way you want. So an example of this is, you can convert your MRC map to an MTZ, and then you've got on-the-fly B-factor sharpening in Qt, which is really handy. Or on-the-fly low-pass filtering, for example, both of which are really handy when your local resolution varies quite a lot from place to place. This is an example where it might be like this, and then you sharpen it a bit, it looks better in that region, it'll look worse in another, so you can use the same map and just do that. Let me see. Oh yeah, and there's an example of on-the-fly low-pass filtering. So you can just filter the map back to 6 angstroms and then go back to your global. Like if you want to see just connectivity or the really disordered parts of the map, you don't want to load in a whole other map, you can just do it all on the fly, which is nice. All right, but if this is with a model placed here, the way I would start if you were planning to build Denovo is to start by placing secondary structural elements, in particular helices. They're the easiest ones to place by far. Beta strands are tricky, and I would deal with those after you've got your helices. Hopefully you've got some helices. So the way to start is you place your cursor at the center of the helix, of the helical density, and you trigger place helix here. I've got a key bound to that, which is H. If you download my key bindings, you just press H, and then it will automatically try to fit a helix to that map. And then what I would do from there is I'd like trim or extend that helix so that locally it takes the entire helical density that you can see there. So like this one, you might want to extend it a little bit to the north, for example, and then real space refine the entire region to adjust the fit to the map, and then start placing side chains. Let me see. Oh, the other thing is I would add secondary structure restraints whenever possible if you're at moderate resolution. They really help with keeping your helices helical and making sure your carbonyls don't flip around all over the place. The other thing is the refinement weight. The lower this is, the more idealized the geometry will be. The higher it is, the more it'll be considering the map. With EM maps, the default value might end up doing crazy things like blowing up your model. So if that happens, you'll want to change this. There is in modern versions, in the latest version of Qt, there's a button to optimize this. That sometimes works, it sometimes doesn't. Often you'll just need to try different values, like even down to like 0.5, 0.2, whatever. It all depends on the scaling of your map. Qt is expecting that your map will be scaled like a crystallographic map, and if it's not, it can get a bit confused. So if your model is blowing up or otherwise behaving weirdly, that would be the first thing that I would check. And this is an example of what real space refinement looks like in Qt. You get this ghost of a model that appears after real space refinement, which you can then drag and move around and try to fit one bit that's out of the density and so on. It's hard to describe, it's easier to show. But, then the question from there is, assigning the sequence numbering. I've got some custom functions which I think make that a little easier, where you can just assign the sequence numbering based on the current position or based on the end of the segment or whatnot, and that makes it easy to assign the numbering, mutate to match the sequence. So just enter your sequence in plain text and mutate it to that. Then test that, see if that matches up to the density, to what you can see in the density. And if it doesn't, you can easily adjust the numbering by 1 or by 2 or by 3 and check if that hypothesis checks out. And then, fit your side chains and try to adjust your sequence register to optimize the local fit to side chain densities. And you use add terminal residue to extend the chain from where you begin. All right. So that's more or less the end of the practical guide part. If anybody's got any questions about all the Qt stuff, now would be a good time to ask them, because I'm just going to go into a little bit of other stuff in a case study after that. Yep.
So, I don't know if you're going to go through it later, but how about model refinement with EM maps?
So yeah.
That's the next step from here. Essentially, you build an initial model.
Yeah.
You need to refine it versus the map and iterate. Correct?
That's right. Yeah, I'm not really covering that in a great deal of detail. The best solution I've found for that, or the most flexible solution, is Phoenix Real Space Refine, which I've found very effective for that and is largely automated. I'm just mostly focusing on manual model building and a little bit of validation because I think that's where the problems tend to arise. All good? Okay. So another alternative to this approach that I just wanted to bring up, I haven't tried this, but I think it's a promising approach in general, is the use of interactive molecular dynamics flexible fitting. There are a couple of different ways of doing this. Tristan Kroll has developed this little plugin, is old, for the new version of Chimera, which looks very promising if you have a machine with a GPU that can run it. And the idea of this is that whereas Qt is only considering local clashes in a linear region of sequence, molecular dynamics flexible fitting, or interactive molecular dynamics flexible fitting, you're considering all the atoms and basically running a local molecular dynamics simulation that you can nudge into the density based on what you can see. And this certainly seems to have given some good results for a couple of tricky cases, notably one of the insulin receptor structures was very much helped by this. as I say, I haven't tried this, but give it a go because it looks really cool and really interesting. And certainly some approach like this, I think, is going to be have to be the future, something that is taking into account geometric considerations of all the atoms that you're dealing with.
How's this different than like Rosetta or any others?
Well, Rosetta is very different because Rosetta. So this is Rosetta. You're dealing with like local sequence fragments, and you're not really. This is using a physical force field and a model of your complete protein. Rosetta is great for building an initial model if you have the computational, horsepower to get it to go. This is more for taking that model and then rebuilding it, rebuilding local regions that are misfolded, for example. I haven't really covered Rosetta because, to be honest, I've never been able to get it to run successfully on a timescale that I like for my particular problems. It works really well for some things. I just haven't had the experience with it to cover it. All right, so the other part that I just wanted to briefly cover is to do with validation, or the other direction of validation, which is the types of errors that you're likely to encounter in macromolecular models, and where they occur, and how to deal with them or avoid them. And so you can largely split these up into things that hopefully will happen at, or hopefully won't happen, but if they're going to happen, they'll happen at the errors of identity, like placing a domain in the wrong density or directionality. Typically, you will only encounter those at fairly low resolution in most cases, so less than 4.5 angstroms. But the ones that I think are really important for medium resolution maps, which are both more common than they ought to be, but also particularly damaging in terms of interpretation, are topology or connectivity and sequence register, because those really affect your interpretation of the model. And at medium resolution, a map where you don't have sequence markers to guide you, they're really easy to encounter, and so there's something to really be aware of. Rotamers, backbone torsion errors, those are only, you're going to get those at medium resolution, but they only really become important at high resolution. Because if you're basing conclusions in your paper off, a rotamer state at 3.5 to 4 angstroms, then, you're already stretching a bit, and you should probably reconsider the way you're writing things. At high resolution, you do need to be careful about these. I mean, you need to be careful about them at any resolution, but the ones that I think are particularly important at medium resolution are connectivity errors and register errors. And so what I mean by register errors are basically where you have the wrong sequence, the wrong local alignment of the sequence to the density map. Which, in this instance, it's super easy to tell that it's wrong, but it might not be if you had, for example, like if you had a couple of these phenylalanines that were spaced equally, you could easily be off by 1 or off by 3, off by a helix turn can quite commonly happen. And so it's something you want to be very aware of. Connectivity, I mean like connecting one helix to another, which which also tends to imply a register error in and of itself. But that can occur even when you can't assign when you're at too low resolution to assign the sequence, you can still have connectivity errors, and those exist in a lot of PDB entries. All right, so how do we deal with these or correct them? So there's no really simple, clean, foolproof way to avoid errors. I would just say to be really careful to analyze absolutely everything as you go. So that means use as many sanity checks as you can in terms of, particularly in terms of like local geometric validation. So check that, so that means checking clashes with null probity. It means checking that your rotamers are sensible with the EM ringer if you're at sufficient resolution for that. And also just checking that the general properties of your built model match up with what you expect. So calculate a hydrophobicity surface. Most of your hydrophobic residues should be in the core, and if you have large exposed hydrophobic patches, there should be a reason for that. Like you have a transmembrane domain, it's going to be hydrophobic. If you don't, and you've got a big hydrophobic patch, then there's probably something wrong and you should take a closer look at it. And fundamentally, I think the important thing is to very carefully go through residue by residue and check the fit to the density, and there's no real way around that. You just have to do it manually. It's really tedious, but it's really necessary. Even if you're at high resolution, things can go wrong, and don't trust auto-built models unless, just don't trust auto-built models. And the other thing is be aware that sometimes you can know that you don't know, and that's okay. And don't be afraid to assign residues as unknown if you're not absolutely sure. I feel like it's better to err on the side of caution and make sure that all of the residues that are assigned in your model are right than risk having some that are assigned that are wrong. And like I said before, I feel like half-map FSCs, which are great for checking whether you're overfitting, these are not really useful for validation of your model as a whole. They don't tell you anything about the local quality or the correctness of the model. And you can very easily build a model which is totally wrong, which still has a pretty decent looking, model map FSC curve, because most of that information is, and it's not until you get to very high resolution that you're going to see any difference with that. For example, there was an example of that actually in that paper about ISOLT, about the IMDFF program, where they did exactly that. They extensively rebuilt the model and corrected a number of errors, and the half-map, model map FFCs looked more or less indistinguishable, despite the fact that over hundreds of residues had different rotamers, and at least 7% were totally in totally different positions. So anyway. All right, so I'm just about done. I know it's a bit early, but I'll just go through a quick example of trying to put all that together into a practical sense. So just looking at model building for RYR1, which I was involved in. When we started, we had a map that was about 5 angstroms, and the prior knowledge that we had consisted of a crystal structure of the first couple of domains and homology models for 4 domains, more or less. And we could identify the fold of the transmembrane region from the density, insofar as it looked like a 6TM ion channel for which there were a lot of models out there. And we knew in the sequence where that was. And so this allowed us to build a polyalanine model, including both all of those known domains and unknown ones that we couldn't build. And as I mentioned, we were lucky in that case because we had a 1,3D class that had a disordered burden, which allowed us to assign the domain boundaries. And so we were able to place, the first that first N-terminal guy that I went through before, and all of these other guys. However, I would say that we actually got something wrong. We were at 5 angstroms here, and we had 3 domains which have identical folds. We assigned them one way around, and it turned out later at when you get to 3.5 angstroms, you can actually tell that 2 of these domains should have been the other way around. I was very confident that it was right, and it was wrong. So it just goes to show you that you can really make errors very easily. And we've since, corrected that record. And as I mentioned, once we got improved resolution, we could do a lot better than that, and we could build a complete atomic model. However, in that case, we were still missing about 1,000 amino acids. So the regions that are highlighted in red here are regions that in the best model until recently we had assigned as unknown residues, because these are in a very repetitive region of the sequence, and the resolution here is poor. And so we couldn't assign them. And so in that case, what we had to do was to go back and see if we could get a better map in that region, because there's just not enough information in the map to help us. So we can have a look at information from 3D classification, which gives us some idea. So this is in this one data set. We can see that this whole region that I mentioned was troublesome for model building is also moving around a lot. So we had the idea that the lower resolution in that region might be due to unresolved continuous conformational heterogeneity of that region. So the solution to that was to apply a focused refinement strategy. So basically to put a mask around just that region and refine orientations just using that masked density. However, in this case, because we're dealing with a tetramer, we need to first perform a symmetry expansion operation so that you're not throwing away 3/4 of your data. And when you do that and perform a mask refinement in C1 with local angular searches, you get much, much better local resolution. And obviously, much worse local resolution everywhere else. Although the rest of the map blurs out, the region within the mask improves substantially. And to give you an idea of that, so this is a region where we actually, where the map was really poor. We could place the domain because we had a crystal structure, but otherwise we wouldn't have been able to build this, because you can see here that the connections between beta sheets are really, really, like the connectivity of the beta sheet is very undefined. Side chains are not obvious, there are cross connections and so on. And the map from local refinement is dramatically improved. And so that allowed us to then build the entirety of the rest of the model. And that's just to say that if you have a region that's really troublesome in the model, you should, in the same way that I feel like crystallographic refinement is an iterative process of improving your map based on your model, for EM you should be thinking about, if it's really tough to build your model, maybe you should go back to your data and see if you can get a better map for that region. And that's really all I have, so thanks very much for listening. And if you got any questions, or if you want to go through anything, any of your own problems, if you got your own data, I'm happy to help.
I guess, how do you know if your resolution is bad just because you don't have enough particles, or because, sometimes you don't have the orientations?
If you got a preferred orientation.
Yeah, and you're not filling out all the angle stuff, so that's not something you can.
That's actually something. There's a great program for that from a writer at SEMC called 3DFSC, which you can use to at least analyze whether that's your problem or not. And that'll give you a description of the anisotropic resolution limits of your data. And that should be able to tell you if that's your problem or not.
And that, because masking wouldn't help in that sort of situation, right?
No, I mean, it's not going to solve your problem. And you'll often also see that from the density. If you have a particularly pronounced preferred orientation, your density is going to look kind of stretched. Like your helices, instead of in cross-section looking sort of circular, will be more ellipsoidal, let's say.
Yeah.
And that's quite common. Sometimes you can fix that in post by getting rid of some of the orientation that is overabundant, either via directly getting rid of them or just via classification. Sometimes that can work to identify a single class which is more or less isotropic, but it's often an uphill battle. And the other way to deal with that in data collection is to collect your data with a tilt, with a fixed tilt, which can give you those orientations back, or just get a better sample. Is the other one. Like use a grid which has a thin carbon layer can be a good thing sometimes, or depends on the situation.
One other question.
Yeah.
When do you, because I know sometimes doing like a bandwidth filter can help, like applying both like a low,
A high pass
high
filter?
pass and low pass
I
filter.
mean, I
don't
haven't.
know.
Yeah. I don't know. I haven't found. I've tried high pass filters. I've never found them especially helpful for visualizing maps. High pass filters can certainly be helpful for visualizing micrographs. For visualizing maps, for visualizing density maps, I haven't encountered that. But you can try that easily enough, particularly if you convert your data to MTZ. Then you can just read in the data from whatever resolution range you want and go with that. And that works fine. But usually, in my experience, low pass filtering is more helpful than
Do you have a program you prefer for local refining? I mean, you didn't mention any program you're using.
Oh, I was using Reliant.
Reliant.
Yeah, but yeah, I'm sure you can do it with FreeAlign as well. I just don't have as much experience with that. CryoSpark, unfortunately, can't do it yet. I really like CryoSpark for a lot of things, but for local refinement, it doesn't work. In fact, for mask refinement in general, CryoSpark isn't really great. It's great for getting an initial map. It's great for getting, but for local refinement, it doesn't quite work. Yeah, so in that case, the thing that I was actually saying here, you really need, so this is using Reliant, and specifically, it's important that you only use, in this instance, that you only use local angular searches, because after you've done your symmetry expansion, you don't want to end up with a case where you have your symmetry expanded copies lining up on one another, like, if you see what I mean. If you're doing a global search, you could end up with these guys getting confused. If you just do a local search, everything behaves pretty well. So this you would be starting from. So you start by doing a global refinement in Reliant. You take the data star out of that. You put that into Reliant particle symmetry expand to generate a symmetry expanded set of particles, which basically just has the same set of particles, in this case multiplied by 4, with one that's the original, one's rotated by 90, 180, 270, and then refine using local angular searches with a mask, and that works really well in my experience. Obviously, if you have an asymmetric complex, you'd do the same thing, but just you don't need to worry about symmetry expansion.
So Oli, you talked about uncertainty with your atomic models. How do you represent uncertainty in your map? Especially if you know you have good data in certain regions with a certain B factor, and the current representation is really just one B factor or one FSC mask.
Well, yeah, that's a good question. I mean, the approach that some people take into that is to filter your map based on the local resolution rather than filtering the overall map based on a single resolution value, which in theory I like, but in practice I don't like the results of anything that I've seen that does that.
Very hard for me to interpret that when I see them.
Well, I could interpret it. It's just that I find that because you'll see one region where your helices are sausages and one region where your helices are really well defined. It's just that the issue that I have with that is often it seems to all the programs that are out there, which seem to be basically based on the same algorithm, which is just a box-wise FSC calculation where you calculate multiple 20 voxel by 20 voxel FSCs. They seem to filter much too aggressively in lower resolution regions, and I don't know quite how to deal with that. But yeah, I don't have a good answer for that. Yeah.
So you mentioned like using EM Ringer and Molprobity as validation tools.
Yeah.
For like Ramachandran angles and rotaverse. I guess I'm not really sure, but I think they look at high resolution crystal structures for like statistical outliers.
That's right. Yeah.
Given like all the improved resolution in EM maps, do you think there'll be like a version of that that's based on EM data at some point, and do you think it'll be different?
I mean, I don't know. I would doubt that it would be different necessarily, but certainly once there are sufficient higher. I mean, the thing is, most of the high resolution data that's incorporated there is really, really high resolution data, like basically atomic resolution crystal structures. Which, I mean, I don't know. Things are moving pretty fast. I don't think we're quite going to get there anytime soon, but I'll probably be proved wrong in the next couple of years. But yeah, like even the best data that's out there is for EM is just breaking 2 angstroms. Well, I mean, from diffraction that's not true, but from single particle at least. I don't know. Do you guys think there's any route to real atomic resolution Cryo-EM?
Need better samples.
Yeah. It's all the user's fault, right? It's all
Yes. Because theoretically, we can go below a half an angstrom.
below half an angstrom.
Does the camera do, I guess?
What would the current? Yes, and we would have to have a major upgraded hardware to go easily beyond that.
Well, yeah. In that case, once we routinely get 1 angstrom or so, then for sure we can update those databases.
But in those cases, you wouldn't necessarily rely on the Ramachandran plot that much because you're going to see.
Oh no. When you're at 1 angstrom, you don't need the Ramachandran plot. It's when you have that information, you can use it to as prior knowledge for other lower resolution situations. But yes, it should be the same from crystal structures as Cryo-EM. I would expect. I can't see any obvious reason why it wouldn't be, but I may be missing something there.
Well, I mean, I would assume so also, but I don't know much about crystallography, but maybe there's some kind of constraints that happen.
I mean, at crystal contacts, yeah, but they all differ from crystal to crystal, so they sort of come out in the wash.
Can I have a question for the
Yeah.
local refinement?
Yeah.
So what's generally the procedure for the local refinement?
Well, that's in what sense? What do you
For
mean?
example, I already have a map, and
Yeah.
for most part, the resolution is high, but for small parts,
Yeah.
the resolution is not very good. And I want to improve
The resolution.
Yes.
So it depends on the situation. If you're talking about a situation where you have a single domain that's, let's say, continuously distributed with respect to the rest of the protein, their local refinement or focused refinement will usually work quite well, assuming that region is big enough.
Okay.
If it's the case that you just have a region that's flexible, that's continuously distributed in shape, then focused refinement isn't going to help you. Because all you're doing is you're considering the orientation of that region and chucking out everything else. And if that region is flexing and bending, then focused refinement per se isn't going to help you. And what you want there is some form of flexible refinement. Methods for which have been developed at the moment, but are not really all that widely available yet.
Okay.
I think Dmitry Taganov might have talked about that. No, he didn't? Okay. Yeah.
If not, you can always email Oli.
Yeah.
Or see him on Twitter.
Exactly. Yep.
Let's thank Oli one more time. So this is the last formal class. Wednesday is more of a wrap-up potpourri if you need anything. We'll be sending out a survey soon, so don't forget to fill out that survey. If you do want to talk about anything specific on Wednesday, let us know, and we can cover anything within that 1.5 hours. Whether it be hands-on, practical knowledge, it's really,
Can I
obvious.
get on Krios?
Get on the Krios.
Ollie, you get crazy in there all the time.